Lecture 7.3, PDE solution by separation of variables. We're now ready to learn one of the most important techniques for solving PDEs, separation of variables. It applies only to linear PDEs since it will require the principle of superposition. Not all linear PDEs yield to this solution technique, but several that are important do. The technique includes the following steps. First, we assume a product solution, okay? So we assume the solution can be written as a product of functions of each independent variable. So say we have time and one spatial variable. So if you've got a spatial variable, little x, you'll say, okay, big X of little x times, say, big T of little t is going to equal the solution of u of t comma x. So this is a product solution, and that's something that we'll need to assume to be the case if we are going to use this separation of variables technique.
How do we know that it's linear or not linear?
It's linear. We had a short discussion of that before. The idea is that u, so like the dependent variable, is dependent or enters the equations linearly. U and its derivatives enter the equation linearly. So you don't have like cosine u. You don't have u squared. You don't have natural log of u. Okay, these would be nonlinear ways of it entering. You don't have 1 over u. Okay, you have u or a constant times u. You could have a derivative of u and then a constant times the derivative of u. But you don't have any nonlinear ways that u, the independent variable, or the dependent variable enters into the equation. Which is a lot of PDEs can be written, a lot of physical modeling situations can be written with linear PDEs. There are nonlinear PDEs, and they are almost exclusive, and there are a few exceptions, but they're almost exclusively solved with numerical techniques because we don't have a lot of tools to deal with them analytically. Just like with ODEs, nonlinear ODEs, there aren't a lot of solution techniques. A few special cases, there are solutions that are known. Otherwise, we just use some sort of numerical approach. You can find out stuff from the phase space as well. So you can look at the like a quiver plot of the phase space of a nonlinear equation. You can find out stuff like, okay, if you have a solution that starts here, it'll move like this. That breaks down when you get to very high order phase space. You lose your picture in your mind of it, but it's still useful. Okay, separate the PDE. So next step, substitute the product solution into the PDE and rearrange such that at least one side of the equation has functions of a single independent variable. If this is possible, the PDE is called separable. Okay? We don't know before we try if it is separable. So we try a product solution, and we see if it's separable. If it is, then we're in good shape. So if you just have on one side of your equation things with x in it, or one side with just t in it, then you have a separable differential equation. Okay, set equal to a constant. So each side of the equation depends on different independent variables. Therefore, they must equal the same constant, often called negative lambda. So if we've got, and I will do an example of this in a minute, if you've got two sides of your equation that depend on different independent variables, the only way that can be true is if they're never changing. Those two sides of the equation have to be never changing with those variables, and they have to be equal to each other. Okay. Repeat separation as needed. If there are more than two independent variables, there will be an ODE In the separated variable, so the separated variable, say you separated t in the first one, and then there was still like x and y or something like that. You can only separate one at a time. So you separate one out, and then one of them is going to end up being an ODE, the one that was separated out completely. The other one's going to leave you with a PDE, and then you can do it again to try to get try to separate that one, that PDE again. So try to continue to separate until only ODEs remain. Okay. Then solve each boundary value problem. Solve each boundary value problem, ODE, ignoring the initial conditions for now. So remember the boundary value problem that we learned how to do in last lecture in 7.2. That's going to show up for every spatial variable. We're going to have a boundary value problem. Okay, so we'll have to do a boundary value problem for x, for y, for z, or if you have polar coordinates in r and theta, etc. Good. Once you've solved those, you can solve the time variable ODE, which you separated the time variable one. You can actually do these in either order. You can do the time variable first if you wanted to. The order of those two doesn't matter. So solve for the general solution of the time variable ODE, sans initial conditions. So we are going to not plug in the initial condition because we want the entire solution to match the initial condition. Okay? So we're going to leave it as the general solution, and then we'll apply the initial condition in a moment. Construct the product solution, multiply the solution in each variable to construct the product solution. So it's this, but with your solutions plugged in for x and t. If the boundary value problems were sturm-liouville, the product solution is a family of eigenfunctions from which any function can be constructed via a generalized Fourier series, which is how we're going to match that initial condition in a moment. It can also have, I mean, it's not guaranteed. If they were sturm-liouville, you know it's going to work. If it's not sturm-liouville, it still might work. You still might be able to construct a generalized Fourier series in a moment from those eigenfunctions. So that's, the sturm-liouville one just guarantees it. Apply the initial condition. The product solutions individually usually do not meet the initial condition. So the product solution that you write here is, it's gonna have a function of time and a function of x, and they'll meet the boundary conditions, but generally they're not going to meet the initial condition. So what we do is we construct a generalized Fourier series of the product solutions. Okay? Superposition tells us a linear combination of solutions to the PDE and boundary conditions is also a solution. So a linear combination of solutions to the PDE and boundary conditions, what we've got for the product solution here, is also a solution. So if you take a linear combination of them, it's also going to be a solution, which is great because you can take a linear combination of them as a generalized Fourier series, and you'll be able to construct any initial condition, virtually any initial condition. So the unique series that also satisfies the initial condition is the unique solution to the entire problem. So that's how we're going to do it. We're going to just say, we're going to kind of like bootstrap our way. We're going to say, okay, let's hope it's separable. Okay, it's separable. And we'll solve each of these boundary condition problems. We'll find solutions that meet the boundary conditions. Then we're going to meet the initial condition by constructing a Fourier series that satisfies that initial condition. And then we'll have our solution. So that's our process here. And we'll see it in an example now. So consider the 1D diffusion equation given in 7.15. So it's a partial differential equation. It is actually something that models heat diffusion, also like chemical diffusion, like any diffusion process can be modeled with this 1D diffusion. with real constant k, with Dirichlet boundary conditions on interval x is from 0 to L. We'll have the 0 boundary have dependent variable 0, and at L it'll be 0 as well. Okay, and with initial condition given here, it's going to be some function of x. So along this line from 0 to L, there's going to be some function of x that'll be describing the initial condition. This, you can think of u in this problem as being like the temperature distribution or something like that. Some initial temperature distribution, and we're going to say that the two ends of the interval are 0, so that would be like 0 degrees. And we're going to see what happens to the temperature distribution over time. Okay? And we'll plug in a specific f at the end of this problem so that we can see some plots. So, okay, assume a product solution. So that's our first step. First, we assume a product solution of the form Tx, where t and x are unknown functions of time and x. Separate the PDE. Second, we substitute the product solution into equation 715 and separate variables. So we just plug Tx in wherever we see u here. And you take the time derivative, which means the x function is a constant in time. So you take the derivative of u with respect to time, or t with respect to time, and then x is still there. And then on the other side, when the second partial with respect to x is taken, it just becomes x double prime, and t is there. The constant is there as well. We can arrange this to be t prime over kt equals x double prime over x. So it is separable. So we have the time stuff over here and the space stuff over here, right? Note that we chose to group k with t, which was arbitrary but conventional. So as we'll see, if we brought the k over here, our boundary value problem would include that constant in it, and we already solved the boundary value problem for there not being that constant in it, and so we like to keep the k with the other one. But it's really arbitrary. Okay, so set equal to a constant. So since these two sides depend on different independent variables, t and x, they must equal the same constant. We'll call it negative lambda. So we have two ODEs here where we have t prime over kt equals negative lambda, and x double prime over x equals negative lambda. They equal each other and they equal a constant. So this upper equation that in time becomes this ordinary differential equation. We just rearranged it. And then the spatial one becomes this ordinary differential equation. Great. So now we're back to ODEs to solve. Solve the boundary value problem. So the latter of these equations, 721, with the boundary conditions, 716, the Dirichlet boundary conditions, is precisely the same sturm-liouville boundary value problem from the previous example, the example from last lecture where we did the sturm-liouville problem for this equation, with 0 as our initial our boundary condition on each side. So I constructed it this way so that we wouldn't have to redo the boundary value problem here. But in general, you have to redo it. But we found in the last lecture that this gave us eigenfunctions given in 722 and eigenvalues given in 723. Okay? So solve the boundary value problem. We get our eigenfunctions and our eigenvalues. Now we can solve the time variable ODE. The time variable ODE is homogeneous and has the familiar general solution. It's just a first order ODE, right? You can integrate it if you want or use any technique of your liking with real constant c. So it's just the exponential here. However, the boundary value problem restricts values of lambda to lambda n, right? So the boundary value problem said, okay, the spatial solution is correct for the boundary value problem as long as this is what lambda is and this is what x is. So lambda has been restricted now, so we'll restrict our time solution to those same lambdas. Okay. Constructing the product solution, then we take our Tn and our Xn, the two solutions, the boundary value problem solution Xn and the time domain ODE Tn solution Tn, and we multiply them together. Okay. This is a family of solutions that each satisfy only exotically specific initial conditions. So you could, if you have like a sinusoidal initial condition, you could construct it with this, right? You could use, oh, okay, look, it's just sine, so when time is equal to 0, this exponential is 1, and then as long as we can, multiply this by some constant to match the initial condition, we're good. But that's very exotic, right? That doesn't happen very often, where our initial condition just happens to be a sinusoid. That's at the right frequency for us. That would be rare. So we just happen to find the sinusoid at the eigen value frequency, eigenfunction frequency that we've got. So what do? We apply the initial condition. The eigenfunctions of the boundary value problem form a Fourier series that satisfies the initial condition on the interval from 0 to L if we extend f to be periodic and odd over x. Okay, so remember, Fourier series only apply to periodic functions, right? So if we have a function that's defined over a finite interval, if we take copies of that and we repeat the function over and over again, so for instance, if you had some function from 0 to L that looked like this, the extension of this that's periodic and odd would look like this on that side, and then this, and then it would repeat, etc. So then you could extend it out. So we say, okay, there's a periodic extension, odd extension, which allows us to write the odd Fourier series synthesis here. Okay, so we can say that f star, the odd extension of our initial condition, is a Fourier series, and the analysis gives us what the coefficients are. Okay, so this is just the standard Fourier analysis, and we chose the sine series because we made it an odd extension. We could have made it any periodic function that just repeated from 0 to L, and we didn't do the odd extension, and then we would have had to do an AN and a BN, but we just arranged it to be convenient for us. Okay, so the complete solution then is going to be a Fourier series, so that uses this this representation. So it says, oh, okay, these Bn components, we'll plug them in here in an infinite sum, and this is a Fourier series that converges to the initial condition. So when t is equal to 0, this term goes to 1, and you have this sum of sine and Bn terms, and the Bn's are chosen such that we satisfy the initial condition over x from 0 to L. And it satisfies the PDE, it satisfies the boundary conditions, because we use the eigenfunctions, and the initial condition. Okay? So that's how we were able to do something that satisfied all of them. Was we were able to use a Fourier series to construct the solution. If we want to plot solutions, we need to specify an initial condition from 0 to L. So we can choose anything piecewise continuous, but for simplicity, let's just say it's just a constant 1 across the interval from 0 to L. So it's at some non-zero temperature, call it 1, or non-zero quantity, whatever U is, and then we'll go from there. So the odd periodic extension is an odd square wave. So the integral Bn can be given here. So this is one that is pretty straightforward to compute what the Bn's are for a square wave. We've probably done that example, actually. That is the example we did, was an odd square wave. So it's all meshing. It's all coming together. And these are the values of Bn for different n values. So now we can write the solution as being, in the specific case of the initial condition f of x being equal to 1 over that interval, we have this, because our Bn's are now 4 over n pi, where n is odd. So you have to, I put that in there because when n is even, you are not including that in the solution. Okay? So plot it up in Python. We'll set k and L to 1 here. So it's called the diffusion coefficient k. We'll set that to 1. We'll set L to 1. And then we'll do 100. So when we want to plot it, we have to do a partial sum, right? We can't sum up to infinity. So we're going to sum up 100 terms, the first 100 terms of the series. And I create an x array and a time array, and I go out just a couple time constants, essentially like the max damping time. So just because I didn't know how long to plot it for, I was just like, oh, I'll go out a couple max time constants here for the decaying exponential. And then I'll initialize my solution array. What I do then is I come through here and I say if n is even, we'll just pass it, which is we don't have anything to do. There's no there's nothing to add here. If it's odd, though, we compute u sub n, which is essentially just the inside of that sum of our solution. And I take the outer product here because I want to multiply each value in x by each value in time and create an array for each value of x and each value of time. There are different ways to do this. The outer product is nice. If you have two arrays that are like n by 1 and 1 by n, or 1 by m, you end up with an n by m. That's the outer product of two arrays. So this outer allows me to do that multiplication. And then let's plot the initial condition first and see what it looks like. Because it should look essentially like 0 up to 1. It's like a square wave, right? We have this ringing phenomenon that's happening here, which is something you're hopefully familiar with or have seen before in doing Fourier series analysis, where next to a discontinuity, you'll get that, and you have to add up an infinite number of terms to get that to go away. So when you have a partial sum, you're always going to get that sort of ringing. I left it. I could have summed more terms here, but I was like, okay, 100 is plenty. And it was fast to do 100. And now we plot the entire response. So I'll use a color plot to show this. And so we have our 0 to L is 1 in space, and we have time evolution. So it starts out at pretty much 1, okay? So it's the yellow color, the light green color. And what happens is immediately the boundary condition, like right next to the boundary, you have this huge, say it's temperature differential between 1 and 0, and immediately heat starts to flow out and the temperature starts to drop rapidly there by the boundary, whereas the temperature of the quantity that's in the center takes longer to reduce, right? And so you get this diffusive effect where heat's flowing out, and it eventually is going to come down to 0 degrees. So it starts out close to 1, and it goes down to 0 as time evolves. And you can go out further, and it approaches 0, and it just sort of settles out there. And that's pretty typical of a diffusive effect, right? If you concentrate something in a box, like say you concentrate a gas in a box, and you have it in a room that's, got some other gas in it or is a vacuum, and you open up the box, well, it's going to diffuse out, right? But it doesn't all instantly disperse. It diffuses its way out to the room. Same with how heat flows. It diffuses its way places. So that is the solution. So we did it analytically with this summation. You can do this type of thing for any, remember, we could have defined any weird initial profile, and we have the solution for it, which is pretty nice. Now let's do a little bit of a thought experiment here. What if we had said, this is a very common problem to do too, what if we had said way up here, I want to know what happens in this bar, but this bar, I'm going to take this L out to infinity, this the end of it. So I'm going to say it's like a semi-infinitely long bar. Okay, that's a common problem to see. What changes, I guess, in this problem? Yeah, so one key thing that we depended on here was that we could do an odd extension of our initial condition from that interval, right? But now that interval has gone out to infinity, and so we can't do an odd extension. What do you guys think we would need to do then? How do you do a Fourier analysis of an aperiodic function? Do you guys remember? Well, usually we would use the complex form, and it's the Fourier, instead of the Fourier series, we would use the Fourier integral, right? Yeah, Fourier transform is typically what we would call it then.
Implies that you use Fourier integral to solve this problem.
Yeah, well, and I don't know if he does the infinite bar, but
Yeah, the exercise you put on the assignment is that one, but the infinite one.
the infinite bar, is it?
Yeah.
Okay, I'll have to look back. But yeah, the infinite bar, you have to write a Fourier transform for it because you can't do the periodic extension. But it's totally fine to do that. So you can construct the Fourier transform instead of using the Fourier series. So that's also a valid approach. And when you get to that infinite interval, you can't do the odd extension, so you're stuck with doing the Fourier transform. And stuck is a little strong because it's actually pretty easy to use the Fourier transform instead of the Fourier series. So, but that was just a little caveat I thought I would highlight. So this is a really powerful technique. It's one of the primary techniques that's used to solve PDE equations. Okay, so to solve PDEs, one of the main ways is to use this separation of variables technique with Fourier analysis, okay, to satisfy your initial condition. Yeah?
I saw in Kreising's book the same PDE equation,
Mm-hmm.
but he used different one after arriving at the ODE, the two ODE. the first one he used this general solution, the suggested general solution form like a sine px, b plus b cosine px.
So he doesn't do the odd extension then. Yeah.
He used that for the L into infinity in this case. You have the initial condition for that problem.
Yeah, I'll have to look and see. I mean, one of the things I would say, the Kreisig text has some really nice examples worked through, but it's only really a handful of them, and then the exercises typically don't have you actually solve your own PDEs. Most of the exercises are having you use a result from the solution that's in the lecture. It's useful to see a couple more worked out examples, but it doesn't necessarily give you a lot of practice. So the other two texts that I included there are, and they have more examples, but then they also have, some of them have better exercises so that you can do your own solutions to different problems. I would say that there are a large number of these PDE solutions that are worked out somewhere. So you might say, okay, you've taught me how to do a Laplace transform, but now there's a whole table that tells me, they've already worked out the integrals and everything. And that is a way to approach this. For a lot of cases, it's already been worked out. Keep in mind, though, that the solution depends on the PDE, the boundary conditions, which are very important, and then the initial condition. So if they solved it for some general initial condition and a boundary condition that matches yours, that's probably a good one for you. You probably can just use their solution for your problem. But it's important to keep in mind that the boundary conditions being different, so to say, like, it's not Dirichlet, it's not Neumann, it's some other mixed one or something like that. Not in every case, you're not going to find it worked out for your problems. You might need to work it out yourself. I think that one of the important things here is to sort of get a feel for how you can approach doing PDE solution, especially the separation of variable concept and the Fourier concept, where you can say, okay, I can take these eigenfunctions and construct a solution that matches the initial condition. That's one of the sort of key ideas here. So there are also some other, really elegant solutions of PDEs that are out there. They don't all depend on separation of variable, but I would say a large chunk of them uses some variation of the separation of variable technique. So, yeah. All right. So I'll do another example on Friday, and then you guys have a homework problem where you do this problem again, but with Neumann boundary conditions. Okay.